Section 1. A River Secret. The Colorado River is one of North America's great rivers. It carved the Grand Canyon. It runs through deserts and farms. It fills big reservoirs that supply water and power for millions of people. One late summer morning, a team of scientists saw something in their data that made them stop. A satellite picture showed the riverbed doing something it should never do. The ground under the river was bulging upward. At first, they thought the computer made a mistake. Satellites give lots of data, and sometimes sensors glitch. But other instruments told the same story. Radar images showed the tiny rise in the ground again. Ground stations confirmed it. Even gravity measurements, which track mass underground, hinted at a change. A rise of a few centimeters might not sound like much, but when a whole stretch of riverbed rises smoothly, it means pressure is building below. That could be from water, from gas, or from hot rock. It could press on buried pipes, on dam foundations, and on the soft soils that hold towns and canals. Because of how serious that could be, the U.S. Geological Survey flew experts to the region. They met with local water managers and engineers. After checking the facts, the USGS issued a red alert. That is the highest warning color. It tells people, pay attention, watch updates, get ready to act if needed. The word alert made many people uneasy. The Colorado River is a lifeline. Any threat under its bed could change how water moves, how much water people get, and whether dams and roads stay safe. This is the start of the story. From one odd satellite reading, a full investigation grew. What the scientists found next surprised everyone, because it mixed clues from many fields: satellites, seismometers, wells, and rock tests. Together, those clues told a story of a hidden system waking up under the river. Section 2. The first signals, how it was found. The first alert came from satellites that measure very small changes in Earth's surface. One of these tools is called InSAR. It uses radar to see differences in height by comparing images taken weeks apart. When the team ran InSAR over a 40-mile stretch of the river, colorful rings appeared on the map. Those rings showed a dome slowly rising under the riverbed. Another tool, Grace-style gravimetry, satellite gravity measurements, showed a tiny shift in gravity over the same area. That tells scientists more than height. It tells them if mass is changing underground. A rise plus a gravity change means material below the surface is moving or changing state. Back on the ground, GPS stations recorded small upward motion that matched the satellite maps. Engineers also checked old survey lines and found the same trend. People who install GPS for roads or mapping suddenly found their instruments were showing unusual movement. Because satellites and ground stations agreed, the scientists brought in extra equipment. They installed more seismometers to listen for small quakes. They rechecked river gauges to see if flows had changed. They measured water levels in wells near the bank. They sampled water, looking for dissolved gases and small changes in chemistry. Within days, the evidence painted a clear picture. The ground under the river was not quiet. It was changing in a way that needed careful study. That is why official agencies moved quickly to warn people and bring in experts. Section 3. Strange tremors, what the seismometers heard. Seismometers are like ears for the Earth. They can hear tiny movements that humans cannot feel. When scientists looked at the seismometer records near the river, they found a strange pattern. Instead of sharp, short spikes that mark regular earthquakes, the instruments logged long, low hum signals. These signals repeated in a steady way. They came with a regular beat, one small pulse roughly every 19 minutes. The pattern was subtle but consistent. Geophysicists call long, low signals by names like long-period events or very low-frequency tremor. These kinds of signals often show up when fluids or partial melts move deep in the crust. They are common near volcanoes when magma moves slowly, but rare in old river basins. To be sure these were real, scientists compared recordings from many stations. The pulse showed at multiple sensors in the same place and at the same times. That meant it was not local noise, like traffic or machinery. The Earth itself was making the sound. The rhythm suggested a steady source deep below, not a single sudden slip on a fault. That gave scientists a big clue. Something was pulsing there. The pulse might be fluid pressure cycles, moving gas pockets, or an intrusion of hot material forcing its way upward. Seismologists ran models to see how different sources could make the pattern. Some models showed fluid movement in a cracked zone could make pulses like those observed. Other models suggested slow slip on a deep fault could shake the crust in a rhythmic way. Each idea fit part of the data, but not all of it. That is why teams kept listening and added other instruments to get more clues. Section 4. Hot water, strange gases, clues from wells. When the seismometers gave the first hint, hydrogeologists turned attention to wells near the river. Many wells are used for farms, towns, and springs. They contain long records of water levels and temperatures. Scientists rechecked these records and then began to sample water. Two clear changes jumped out. First, water temperatures in several deep wells rose. Wells that had been steady at about 18 degrees climbed to 24 to 28 degrees in a matter of weeks. Second, the chemistry changed. Lab tests found a rise in dissolved carbon dioxide, CO2, and tiny amounts of helium and sulfur compounds. Carbon dioxide in groundwater can come from many sources. Plants, soil microbes, and decay can add CO2 near the surface. But helium is different. Helium, especially certain isotopes, often points to very deep sources, even the mantle beneath the crust. Sulfur-bearing compounds like hydrogen sulfide or sulfates can come from heated rocks and hydrothermal fluids. To be safe, the scientists checked for contamination from industry, gas wells, or natural oil seeps. Those checks did not explain the pattern. The gases seemed to come from depth and to be moving up toward the surface. Hot water and deep gases together formed a strong hint. Something was delivering heat and deep fluids upward. That could be a rising pocket of hot rock, or it could be warm fluids pushed up by pressure changes. Either way, the riverbed was the place where these deep signals arrived at the surface. Section 5. Modeling the dome. What could make the ground rise? With InSAR, GPS, seismic, and well chemistry lined up, modelers went to work. Their job was to test what kinds of underground scenarios could make the dome shape, the rhythmic tremors, the warming wells, and the gas release. One model tested the idea of a magma intrusion. Magma is molten rock that rises from deep in the earth. If a pocket of magma moved upward and pooled under the riverbed, it could lift the ground and warm the water. Magma also releases gases like CO2 and helium when it decompresses. However, the models that fit the uplift required magma to be quite deep and comparatively small. If that magma were close to the surface, an eruption might be possible. But models showed no strong surface heat signal yet, and remote infrared cameras did not show any hotspots at the river. So magma was possible, but not an obvious match. Another model looked at pressurized fluids. Large reservoirs of warm water or gas can sit in layers of rock. If new pressure pushes those fluids into nearby cracks, the rock can swell like a balloon. That swelling can make a dome and cause long-period tremors. This model matched the rhythmic pulses well because fluids can move in pulses as pressure waves travel. The gases observed in the well water also fit a fluid model. A third option combined both ideas, heat and fluids together. Hot rock could warm deep fluids, raising pressure and forcing gas-rich water into shallow layers. Faults and fractures could then guide the fluids to the riverbed, producing uplift and tremors at the same times. Modelers compared each scenario with the real data. No single model fit every detail perfectly, but a hybrid model, warm rock plus deep fluids moving along a weak zone, matched many of the observations. That became the working hypothesis. A deep, warm system was changing, sending pressure, heat, and gas upward along a buried pathway under the river. Section 6. Field teams go to work, drilling and mapping. Models can tell a story, but scientists need real samples. So field teams drilled a few shallow cores and set up borehole sensors. Drilling under a riverbed is not easy. The river moves, sediment shifts. Still, scientists used carefully planned sites on dry banks and islands to reach deeper layers. Cores revealed layers of sand, silt, and older gravels. In a few places, cores hit zones of fine clay with veins of mineral alteration. Those veins had minerals that form when hot fluids pass through rock. The altered zones extended at depth, meaning fluids had flowed there in the past. Borehole temperature logs confirmed the warmed water. Downhole sensors measured pressure pulses that matched the surface tremor timing. That was a key link. The pulses seen on seismometers were the same ones felt as pressure waves in the boreholes. That tied the surface uplift, the tremors, and the fluids into a single system. Teams also ran portable magnetics and resistivity surveys. These tools can map underground structures without deep drilling. They found a zone of lower resistivity under the dome. Low resistivity often points to warm, saline fluids or partially altered rock. That gave another sign that fluids were present in a broad volume beneath the river. Taken together, the field data made the models more likely to be correct. A deep, pressurized fluid system, warmed by nearby heat, traveling along weak rock under the river. Section 7. The red alert explained why officials worried. With real cores, borehole data, and satellite maps in hand, officials had to decide what to tell the public. The USGS and water agencies faced a hard question: how to warn without causing panic. They explained the real risks. First, shifting ground can stress infrastructure. Dams, bridges, canals, and pipelines crossing or near the river rely on stable foundations. If the ground under them changes shape, those structures can crack or leak. Even small seepage can widen and weaken a foundation over time. Second, pressurized fluids and increased gas flux can change how groundwater behaves. Aquifers might lose water if pressure paths open and drain water somewhere else. That can reduce water supply for farms and towns. Third, if faults under the river become active, they can cause earthquakes. Even small quakes can damage older structures. In a river valley, landslides or bank collapses could shift the channel, affecting water flow and habitat. Officials framed the red alert as a call for careful readiness. They did not order mass evacuations. Instead, they urged water managers to check dam monitors and inspectors, to survey critical bridges. They asked communities to prepare emergency kits and to follow official channels for updates. The alert also unlocked extra resources. National labs and university teams flew in equipment. Engineers ran stress tests on dams and key bridges. Water managers checked plans for alternate supplies. Everyone moved quickly, sharing data and test results in near real time. Section 8. Theories tighten: magma, fluids, or faults. As more data arrived, theories narrowed but did not vanish. A few things became clearer. Magma intrusion was still possible, but it seemed unlikely to lead to an eruption in the near term. The heat signature at the surface was weak. If magma were present, it was deep and probably cooling as it rose slowly. That scenario could still cause uplift and gas release, but a surface eruption would need more magma moving upward and more heating at shallow depth. A fluid-driven model looked stronger. The pattern of pulses, the borehole pressure waves, the gas chemistry, and the resistivity low fit a picture of warm, gas-rich fluids moving in a shallow crustal pathway. Fluids can build pressure slowly. If a plugged channel opens, pressure can release suddenly and cause small quakes and rapid changes in groundwater. Fault reactivation was also part of the story. Old, buried faults exist beneath river valleys. If pressure from fluids or heating shifts stress on those faults, they can slip. Small slip events can create more pathways for fluids, creating feedback loops that amplify motion. So the most likely scenario looked like this. A warm, deep fluid system has been slowly pressurizing. The pressure found a weak zone, perhaps an old fault or fracture network, and started pushing fluids upward beneath the river. The moving fluids made long-period tremors and pushed the ground up. The gas and heat that came with the fluids warmed wells and changed chemistry. That working model matched many observations. It still left questions. What caused the pressure to change now after centuries of quiet? Did deeper tectonic stress play a role? Was there a tiny melt body adding heat? Scientists kept testing to find the trigger. Section 9. Community response: water, power, and people. When science meets daily life, the questions become simple and urgent. Farmers asked if their wells would dry. City water managers asked if reservoirs could lose water or become contaminated. Power operators worried about canal intakes and turbines. Emergency teams organized open briefings. They told people practical steps: check your well water, take non-perishable supplies, and know 2 ways out of your town. Water managers ran tests to detect sudden drops in reservoir levels or new turbidity in the water. Farmers prepared backup plans. Many farms have 2 or 3 wells. They checked flow rates and lined up portable pumps. Small towns tested their backup power and communications. Schools prepared simple shelter plans if an evacuation were needed. The work of local engineers helped everyone feel safer. Inspections found a few small cracks in older concrete near the river, but none were catastrophic. Crews strengthened vulnerable slopes and placed extra monitoring sensors on critical bridges and dam foundations. Across the region, people talked and worried, but many also felt reassured by the steady work of scientists and engineers. The message repeated in the briefings: be ready and informed, not panicked. Section 10. Past clues. Did the river remember? Scientists scanned old logs and data archives to find if the river had given hints in the past. In some places, decisions from decades ago suddenly looked like early signs. Old seismometer records showed occasional low-frequency tremors a few times in the last 50 years, while some towns had recorded slight warming in unusual years. Indigenous oral histories and early explorer notes mentioned odd hot springs or bubbling spots long ago. These past clues did not point to a clear past episode like the current one, but they did hint that the geologic system had moved slowly over time. In other words, this event might be the most intense phase yet of a long-lived, low-grade hydrothermal system. That idea helped scientists think differently. Rather than expecting a single dramatic trigger, they started to look for slow drivers: a long-term shift in groundwater flow, a change in regional stress from plate forces, or a small influx of heat from deeper crustal processes. The past data told them Earth's processes can take decades or centuries to build to a point we see in weeks. Section 11. Escalation and control measures. Over the following weeks, the system pulsed. Sometimes the uplift slowed for days. Other times it sped up. Minor quakes grew in number but stayed small. River managers monitored turbidity and sediment loads in the main channel carefully because sudden bank shifts could muddy the river and clog intakes. Because the risk of damage to structures remained, engineers took specific precautions. At critical dam gates, they tested seals and emergency release mechanisms. At pump stations, operators put spare parts and backup power on standby. Bridge inspection teams checked piers below water for new scour or cracks. Scientists also ran stress tests in their models to see what might push the system to a worse state. They found scenarios where a very fast pressure release could make a localized ground collapse or a small swarm of earthquakes. Those worst-case scenarios were unlikely, they said, but worth planning for. The red alert remained. Officials emphasized that staying prepared and informed was the best defense. They promised to lift the alert when the data showed steady calm. Section 12. The uncertain ending, learning and watching. Months later, the system had calmed somewhat, but not disappeared. The most intense pulses had faded. The uplift rate dropped, but remained measurable. Scientists were not alarmed as much as they were humbled. Nature had shown a behavior that mixed elements of hydrothermal systems, fault stress, and shallow crustal fluid flow. The work did not end. Surgeons of the Earth, scientists and engineers, set long-term monitoring plans. More boreholes were installed with real-time telemetry. Satellite passes were scheduled more often. Universities began long studies to understand slow-moving systems in old basins. The data from this event would teach people how quiet basins can become active under the right conditions. Local communities found life moved on with a new respect for the river. Water managers added redundancy to systems. Engineers planned for more frequent inspections. Residents kept a simple emergency kit ready and stayed connected to official channels. The final lesson was both practical and larger. The Colorado River is not only a water source, it is part of a living Earth system. That system can shift and change in ways we do not always expect. Science can watch and warn, but it cannot stop nature. The best approach is to stay informed, to prepare, and to let the work of learning continue. Section 13. What you can do. If you live near the Colorado River or depend on it for water or work, here are clear steps you can take now. 1. Stay informed. Follow official USGS updates and your local water and emergency management pages. 2. Make a simple plan. Know 2 routes out of your town. Have an emergency kit with water, snacks, flashlight, and batteries. 3. Check your well and water systems. If you rely on a private well, test it if you notice changes in taste, smell, or pressure. 4. Support community checks. Volunteer to help check on neighbors who may need assistance preparing. 5. Share accurate information. Help keep social media clear of rumors. Share official links and verified updates. If you found this investigation helpful, please like the video and subscribe for updates. Hit the bell so you get notified the moment new data comes in. We'll keep following the science and bring you clear, calm updates as experts learn more. The Colorado River has carved deep history across a dry land. It feeds farms, cities, and life. When the ground under that river moves, it reminds us the planet is not static. It's alive with processes we can study and learn from. The better we study them, the safer we all can be. Stay curious, stay prepared, and subscribe for more science-driven stories that explain how our planet works.